Hello guys and welcome back. So first thing I gotta tell you, you'll notice that I'm in a very different place. Chances are it's a lot more echoey. I'm at the university, so I gotta be slightly less animated and loud because there are people outside of this room studying. So this video is going to be about the laws of physics, and I guess you could say I'm working towards a simplified law of the universe. Okay, I'm boiling everything down to its basic. All right, so in order to start, I guess to introduce this concept, the first thing I would say is so many of these basic laws of physics are all attempting to calculate the exact same thing. The force behind a change. The force that went into a change that occurred, giving a number to a differentiation. This minus this equals that. Ultimately, that's what all of these equations are trying to calculate, only it's not typically minus. So, I'm going to start by going through a number of equations. The first one I'm going to be doing here is called Ohm's law. It's the one I'm the most knowledgeable about, so I'm going to start with it. If you're already fully familiar with Ohm's law, you can kind of skip this part. Okay, so here we go. Where's my mark at? I guess I got this whole board. All right. So first, we got, is that even showing? Ohm's law. I can't tell if you can read that, but I couldn't tell last time either. So we start with Ohm's law. Ohm's law is used to calculate circuits, electronic circuits. No, I'm not going to draw one because it's been a very long time. Now, what is Ohm's law? Ohm's law is V equals I times R. That's Ohm's law. V equals I times R. I can't remember where my camera's at. So, V represents voltage, I represents current, and R represents resistance. Right? Now, what is voltage? Voltage is, you could call it the power source. You've all heard the expression 9-volt battery. You know batteries are measured in volts. It's energy output. It's the force that goes into a change, right? What's current? Represented for some stupid fucking reason as an I. Current is probably exactly what you think it is. Current, like in water. Current is when you take your multimeter, which has 2 prongs, it's a tool used for measuring this kind of thing, and you go bink, bonk. Use these 2 points, and you differentiate them. You take this space in between, and you count the number of, I'm pretty sure it's electrons. You count the number of electrons in here. It gives you a range. So current is the object in motion. Current is the flow. It's what is contained within the 2 points. It's the differentiation between this point and that point. What is in there? Then you have resistance. Resistance doesn't take a rocket surgeon to figure out. It's resistance. The word kind of gives it away. But specifically, what is the resistance in an electronic circuit? Well, the resistance in an electronic circuit is friction, in a sense. Sort of like how the resistance to any motion is friction. So, think of it this way. You have a straw. I forget where I heard this, but I didn't come up with it. It's just perfect to describe this. You have a straw. You blow into this end with 10 psi. I was going to draw a little head there blowing into it, but it would have looked like a dongus. So you blow into this end with 10 psi. You register on this end 8 psi coming out. So if 10 psi goes in and 8 psi goes out, there's a differentiating factor of 2 psi. So resistance has caused a decrease of 2 psi through the friction and shape and energy displacement of forcing a gas, which is oxygen or air, through a solid that limits its expansion. These numbers and figures are irrelevant, but the differentiation between what goes in and what comes out, that's resistance, whatever factor of change has occurred. So, in order to get a numerical value for the force that causes change, or voltage, you need to calculate the differentiation between 2 points that the voltage is acting on. So take any 2 points that the voltage is acting on, calculate one, calculate the other, and then see the difference. And you multiply that or increase it by a factor of the resistance or opposing force. So voltage is going like this. What's stopping voltage? Well, I suppose it's going like this, because typically circuits are indicated as kind of square. So if I measure here, and I measure here, and there's a difference, resistance has caused that. In this particular case, it would be the thickness of the wire, similar to the thickness of a straw. So, in order to calculate the force behind a change, you multiply a sample of the change by the force opposing the change. That's what Ohm's law is. Now, that's the one that I know the best, so that's the one that I went into great detail with. But I will clean this whiteboard properly with an eraser when I'm done. Don't worry, I'm not that guy. So now we have Ohm's law, right? There's more. This one is arguably the most common law that people know about, because typically they don't actually know it. And the fact that people keep accusing me of not knowing it because of the simplicity with which I phrase it speaks volumes about the elitism in academia. Anyway, I would like to indicate right now, I would take this moment to indicate black and white that, did you know, physics used to be referred to as natural philosophy? And now it's kind of a catch-all term to describe various academic disciplines that are mathematic in nature, but don't have their own specific discipline. Why do you think there's so many? There's astrophysics, there's, I forget what the earth physics is called. There's environmental physics, there's electrophysics, that's not really what it's called. Electromechanical technology, it works in a way similar to physics, it's called physics. The fact that I go up to somebody and I say, yeah, I know a little bit about physics, I learned a little bit about physics in school, in that school that I went to, they say, oh, well then you know all about velocities and gravity and that, and you can calculate them. I'm like, well, yeah, but that's not what I learned. What I learned was this kind. I learned electronic physics. Other people learned other kinds of physics, and I thought, what's the difference? And I chased this down and I realized there fucking isn't one. Okay? They keep rehashing the same equation, calling it a new variable, throwing their name in front of it and calling it Planck's law. So let's move on beyond Ohm. Next we have, who are we going to go with? Let's go with Newton. And I'm only going to, in this particular moment, discuss Newton's second law, which is the actual equation itself, which you've heard of, I'm sure. Newton's, see that? I started doing the S as an apostrophe, sort of like that. Newton's law. Hang on. Second law. So Newton's second law. Force equals, what was it? Oh yes, mass times acceleration. Force equals mass times acceleration. Now I would like to take this moment again to give you another disclaimer. My theories have been very numerous and very expansive and breaching all kinds of different topics, but they all seem to line up with each other. So, that being the case, please forgive me if I keep calling this M matter, because I mean mass. This is mass. If I refer to this as matter at any given time, I've misspoken. It's mass, okay? So, force equals mass times acceleration. Or in other words, input causing change is equal to, acceleration in this case would be the current, a differentiation between 2 points, represented numerically, increased by a factor of resistance. F is the force causing change. A is the sample of the change occurring. And M is the opposition to the force. And given the nature of multiplication, this is the way it's typically presented, but it's very easy to just do this. F equals A times M. Force equals acceleration times mass. Acceleration increased by a factor of mass. Now, Newton's law. We're done with that one. I made my point. Newton's law. Hey boys and girls, Drowned Will here with a little adjustment to make. You'll notice that I keep using the speed formula. Distance, oh that's not a good marker. Oy. Distance equals speed times time. You'll notice that sitting on my board whenever I'm talking about this. I was struggling with it for a reason. That doesn't apply here. It doesn't apply here. This whole equation, the purpose of it is to quantify something that's already been measured in a different way. It's kind of a conversion of units or a meshing of units. Speed and time together make distance. You just put a little slash between the two, speed and time. That's how you represent a speed, 8 kilometers per hour, right? So this one does not apply. I really can't go back and redo this whole video again, so please, whenever you see this on my thing, disregard. Ultimately, I do want to point something out to you. First, I hate hunching. Second, but you works with the camera angles you got. Second thing I want you to keep in mind, voltage equals current times resistance, right? Then you got force equals acceleration times mass. You'll notice these two are the same. They're trying to calculate the force behind a change that has occurred. These two are the same. They're a range of the change occurring. They're a snapshot of infinity, if you will. And then those two are also the same. They're both resistance. Mass and resistance are both the opposing force to the input, the force causing change. So, having realized this, I found myself thinking rather obscurely. I said, okay, given Stephen Hawking and Albert Einstein and yada yada yada, and how typically they say, if you want to find, that's too high. This is a dimension, right? Just imagine that's a dimension. To find another dimension, you go put another line adjacent to it. That I'm super belittling his point, but that's what Stephen Hawking did when he said, okay, here's time. Time is a line. And I theorized that this is imaginary time. And then he went real deep into this, and I can't even comprehend the equations, but that's how it started. So I found myself thinking, if this represents all the change, if these two things both represent change, let's consider just what happens if I do this? If instead of going this way, I go this way, straight down, equals. This is experimentation, you see. So I'm looking at this. If these two are the same, I think, what is current squared? I can't remember, it's been too long. Is current squared a thing? It turns out, and I might get this a little backwards, current squared times resistance equals power, I believe. Yes, I believe that's it. I might get these 2 points mixed around backwards because I don't have access to anything to check my work right now, given the room I'm in. So, current squared increased by a factor of that same resistance equals, I'm pretty sure, power. If it's not power, then it's power loss. And then the other one's the other. Apologies for that. So what is power? Power is when you have this whole circuit, and here's your resistor. Power is what happens if you take a wire after the battery and after the resistor. Take a wire off of here. That is power. That's what's actually being used. That's what comes off. And then, okay, so if that's multiplying these two equals, although you have to also include resistance because opposite reaction, that's power. And then these two multiplied together, what's resistance squared times current? Well, so then the opposite of that, R squared multiplied by current, that equals power loss. I don't remember any of the words for this, and it's very possible that these two are backwards. But the point is, current squared and resistance squared are something. I'm still working on that whole theory. That doesn't necessarily mean anything. If you know anything about physics and electronics and something, and if you see where this is going, if this gives you an idea, drop it in the comments, boys and girls. All right, that's gonna do it. Again, please disregard all of the distance calculations you see going forward. Carrying on. So, we got force behind the input, 1. Differentiation between 2 points, 2. And opposing force, 3. Over here, we have force behind a change, 1. Differentiation between 2 points, 2. Opposing force to the change, 3. And all of these are the same. Every single one of these exists so that some douche could put their name on top of a law and come up with their own unit of measurement, like ohms or newtons. It's the same equation. They're trying to solve for the same thing. All of these equations are trying to solve for differentiation, trying to give a numeric value to the difference that we can perceive but not fully comprehend. Because of this, I think this is the essence of kind of everything, of every change. Everything you have ever experienced has been a change. If it didn't change, you wouldn't experience it. If it wasn't differentiated from everything else, you wouldn't be able to tell what it was. Let's use this section right here, of whiteboard, as an example. What can you tell me about this? If this was the only thing that existed, what could you tell me about it? Absolutely nothing. It's white. What is white? I don't know what that is. That doesn't make any sense. What do you mean? What is white? What's not white? Well, nothing is not white. Everything is white. Well then, what is white? You understand? You can't use a single variable to calculate something. So all of these things are trying to calculate the scale behind a force. Force causing change is equal to energy differentiation across 2 points increased by a factor of or multiplied by the opposing force. The simplified law of everything, the simplified law of energy in relation to motion. So, let's use this to calculate something. Something I haven't thought about already. Let's use a sense. What sense can I use? Let's use sight. Let's calculate the force at which I see things. Okay, so let's get rid of all of this garbage for now. Don't worry, like I said, I'm gonna go get an actual eraser in a second. So, using this equation, what do we want to calculate? The force at which I see. So, in order to calculate the force at which I see, which I'll call x, I first need to decide what energy was input into the force of sight. What's the differentiation between 2 points when it comes to sight? Well, seeing is absorption of light. So, the force of the absorption of light would be, I don't know, but I'm going to say the speed of light, I think. The force of the absorption of light would be the speed of light, which I guess would be c. Einstein says it's c squared, but I'm not entirely sure about that. I think, no, the force of light would be c squared, but this, okay, anyway, we'll call it c for now. Multiplied by the opposition. What is the opposing force to the absorption of light? I guess it would be the reflection of light, because light is a constant. So again, it would be c. or x equals c squared. Oh, see, that's I just kind of calculated the speed of the force of light. I realize that it's already been calculated. Einstein already did that, but the fact that I got there on my own kind of validates my theory. Let's come up with something else. Let's use something else. So the force at which I see is, which I suppose would actually be negatives. Would it? Yeah, I think so. Yeah. Oh, would it be c squared and negative c squared? It might be. It's been a while since I multiplied exponents. Either way, you see what I'm going for here. That was a bad example. I am not too familiar with the speed of light. Let's go with, well, let's look at it this way. I just tried to prove it with algebra and things to that effect, right? Algebra, math, my limited understanding of electronic engineering, okay? Now, if that's true, it should apply to every single force of change, right? That's what I'm saying. So let's go with, have you ever heard the expression, you learn more or change more from failing than from succeeding? Why do you think that is? This kind of answers that. If it's most easily described through the use of lifting weights, right? Let's say I have a strength of 8 pounds of something. I don't bloody know. The units don't matter. I have a strength of 80x. I have the ability to lift a weight of 80, let's say. I'm getting a little bit confused. Now, what I actually lift only weighs 20 pounds. If what I'm actually lifting only weighs 20 pounds, that's only weighs 20x, sorry. That's 60 units of x that have gone unused. I have not strained myself enough, and thusly I will not get that much bigger. But if I lift something that takes, if I still have 80x of force available to me, and I try to lift something that is 100x, a much greater change will occur because I am very easily capable of using all 80x of my strength. This one you are not capable. This one you are. Thusly, by struggling against a weight you can't lift, you can use all of your strength and increase it. It's the same thing with anything. The stronger your opposition is, the more you change, the stronger the force behind the change is. How do we calculate the force behind us living and changing? Well, let's start with physicality. So the force of growth is equal to the differentiation between 2 points. So let's say how tall I was how tall I was last year and how tall I am this year. So your range, which we'll call T for tall. T over T or whatever for tall over time. I don't bloody well know, but you multiply that by the force of opposition to growth in life, which I suppose would be decay and death. So we'll call that D. If you can give me the amount of energy that you consume, no, I'm looking at this one. If you can get any of these two variables, you can calculate the other one. If you can give me the differentiation in my size and multiply that, increase it by a factor of the rate of decay or shrinking, you get total force behind growth. And this theoretically also explains why old people start to shrink, get a little bit shorter, because decay begins to overpower the differentiation in growth. Or no, the decay begins to overpower the strength of growth, and therefore, tall goes down. Right? Now, I don't know whether or not to make this a video, put this into this video, or to make another one, but I've realized something. And so how can you use this information? Well, if you want to change as much as humanly possible, find somebody who's going to fight you on it. That's about it. That's about the extent of it. If you want to change as much as possible, find somebody who feels the opposite way very, very strongly, and you will change. Whether towards them or away from them, I couldn't tell you, but you will change.